Welcome back in the lecture series of Halliday, Resnick, Krane, Volume 2. In this video lecture, I will discuss MCQ solution of chapter number 34, that is Faraday's law of induction. So let's begin. Question number 1 is, a uniform magnetic field V perpendicular to a wire loop varies with time as shown in figure this one. Which of the plot in figure 3420b represent the induced current in loop as a function of time? The situation is given this graph in which the magnetic field is increasing linearly with the time, and after a certain point it's becoming constant with time. And these graphs A, B, C and D are basically representing that which one graph is the correct for the induced current in the loop. If the magnetic field is increasing linearly with time, so it means that strength of magnetic field is increasing with time, so it means that current is also increases, because the induced current in the loop is directly proportional to the strength of magnetic field. So option B is the correct option, because here the induced current varies linearly with time and it's becoming constant at the same point when the magnetic field is constant. Question number 3 is, a flexible wire loop in the shape of a circle has a radius that grows linearly with time. There is a magnetic field perpendicular to the plane of the loop that has a magnitude inversely proportional to the distance from the center of loop. Magnetic field is directly proportional to 1 by r. How does the electromotive force vary with time? Options are, it's directly proportional to the time square, it's directly proportional to the simple time, or it's directly proportional to the square root of time, or electromotive force is constant. This is the circular loop of radius r and magnetic field is increasing linearly with time. In the question it's given that the radius grows linearly with time. So it means dr by dt is constant quantity. Secondly, it's also given in the question that magnetic field is directly proportional to 1 by r, so it can be written as B of r is equal to k by r. We know that the induced electromotive force is equal to n d phi by dt, that is the rate of change of flux, and flux could be written as B dot delta A divided by dt. So now we have to find the dA. The area of this wire initially is pi r square, but when the radius of the wire loop is increases from r to r plus dr, then what we get, d of A is the change in area. This is pi r plus dr, because the radius of the second loop is r plus dr, so pi r plus dr whole square minus pi r square. So when we are opening this equation r plus dr whole square, we are using the formula a plus b whole square. So a square plus b square plus 2ab we are using here, minus pi r square as it is. So after simplifying this equation, we get pi r square plus pi dr square plus 2 pi r dr minus pi r square. Pi r square will be cancelled out from the pi r square, and we know that here the dr is very small, further decrease, that's why we are taking as 0. So we are having dA is equal to 2 pi r dr. Now we are putting the value of dA into this equation, that is the equation of electromotive force. It's equal to d phi by dt, that is the rate of change of flux. So B dot 2 pi r dr divided by dt. B is equal to k by r, so we are putting the value here k by r. This r will cancel out with this r, and it was also given in the question that the dr by dt is constant, so this is overall the term is constant, so electromotive force is constant. That's why option D is the correct option. Question number 4 is, the magnetic flux through a wire loop changes by del phi b in a time delta t. The change in flux del phi b is proportional to the current in the wire, the resistance of the wire, the net charge that flows across any cross section in the wire, or the potential difference between any two fixed points in the wire. And by using Ampere's law, we know that integral closed integral B dot dA is equal to mu naught I. So magnetic flux is equal to the flow of current. So option A is the correct option.